In this final subtopic of today's lecture, we will see how do we interpret IR spectra. As we said, IR spectroscopy really deals with bond vibrations, which means that the things that we're going to be looking at in our IR spectrum will be the vibrations of specific bonds. And the bonds that we are going to look at are basically the functional groups that we've seen as important in the reactivity of molecules. And so each functional group has its own signature. In the IR spectrum. And I will give you some of these positions. On your exams, you will be provided with a table that lists all of them, so you need to remember them. But for example, CO double bond carbon group has a very strong vibration between 1630 and 1820, centered around 1700. And so that's a very good sign for carbon. And amino group, for example, will have vibration between 3100 and 3550. And this will be a medium to strong vibration. If we have a carbonyl aldehyde, the CH bond will have very specific vibration around 2720, and this will be a strong vibration. So this is very characteristic not only of carbonyls but also of aldehydes. We can identify both of these parts at the same time. An OH group present in alcohols or water will be about 3200 to 3650, and this is a strong and broad vibration. So this is also very characteristic. CC triple bond, in cases when it's not symmetrically substituted, is about 2100 to 2250. It's pretty diagnostic, but it can often be very weak or even invisible, so that might be a problem. CC double bond is 1600 to 1800. It's normally a relatively weak vibration, but depending on the substitution, it can go to medium. And interestingly and very usefully, the CH bonds, they absorb in different regions depending on the hybridization of the carbon right next to them. They're all kind of medium to weak intensity vibrations, but the sp3 carbon bound to hydrogen will be 2850 to 3000, so below 3000. sp2 carbons, their CH bonds are between 3100 and 3000. And finally, sp carbons will be around 3300, and they should actually be relatively strong vibrations, so medium to strong. Okay? And so what we do basically is we look for these specific pieces of information in our spectrum and try to piece together the structure coming from. Now, our IR spectrum does not include only these things. So if we just draw a schematics of an IR spectrum, then on our x-axis will be wave number. And this will start about 4000, goes 3000, 2000, 1000, and it will end up somewhere around 400. Our y-axis will be transmittance. And transmittance is basically, it's expressed in percent. It's basically the percentage of light that went through. And so most of our IR spectrum will not have any absorption. So we'll pass the light and no light will be absorbed. And transmittance will be 100%. But at some point we will have a bond which will absorb something, and then we'll get decrease in transmittance or increase in absorption. And that will indicate that there was something that it absorbed. We can keep going, and so on. And so we'll get something that looks like this. So the IR spectra are not only upside down, but they also they start at high numbers and go to low numbers. And this is purely for historic reasons. Okay? Now this region, which I haven't really indicated too well, but it's between 1500 and 400 reciprocal centimeters, is known as the fingerprint region. Now this region is very complex. It has, there are a lot of CC vibrations. In each molecule we have a lot of CC and CH bonds, and there are a lot of these complex vibrations there which give rise to this fingerprint region. And analyzing this region, piece by piece is almost impossible. So in most cases you simply ignore it. And in our analysis we will also ignore it as well. However, one needs to know that fingerprint region is called fingerprint because, just like with fingerprints are for humans, fingerprint regions for different compounds are all different. So there are no two compounds which have the same fingerprint region in the IR spectrum. But if you're going to extend this analogy between humans and the IR spectrum, you can think about this as analyzing crime scene. Sometimes you have fingerprints on crime scene, and yes, you can compare that to the database of fingerprints, and you can identify a suspect that way. But the problem there is that you need to compare this with really large database, and also that your suspect might not be in the database. Okay, but sometimes the suspects leave much more obvious clues, some sort of like leaving a business card or a crime scene or something. And these clues, these obvious clues, are presences of functional groups, and these are the vibrations which will allow us to quickly identify our compound. Using the fingerprint region, we could do it, but it was much slower. Okay. Now, in the next couple of slides, we will look at some experimental IR spectra, and I will highlight the features that we've seen so far in those IR spectra. Bear in mind that those will have a white background, so it will be quite a contrast going to the next slide. Okay. All right, so in our IR spectrum here, the first IR spectrum is that of 1-octine. So this is an alkyne, and in this spectrum we can see this vibration between about 2200, which comes from the alkyne triple bond. We notice that this vibration is relatively strong, so it's not weak or an almost non-existent one that we've seen before, because this is the terminal alkyne. And we know that this is a terminal alkyne because we also see at about 3300 the stretching vibration for the CH bond. Since it's an octine, we will also see some vibrations that come from sp3 carbons and hydrogens slightly below 3000. And then the rest of our spectrum would basically be a fingerprint region, which is not very easy to identify. Okay, so from this IR spectrum, we would be able to figure out three main things: that we have a triple bond, that our alkyne is terminal, and that our alkyne has some alkyl substituents as opposed to vinyl or aryl substituents. Now, this will still leave us with a large number of potential candidates, and IR honestly will not be able to tell us between this. Mass spec will help because it will tell us what the mass of this molecule is, and we will see in the next lecture that NMR will help a lot as well. If we look at toluene, this compound we will not talk about too much because it's subject of 3332, but things that we can see are these CH3 groups, which again are showing up below 3000, but we also see something above 3000 right here, which is coming from the CH vibrations in aromatic rings, which are sp2 carbohydrate carbons. Let's look at some more groups. If you look at decane here, decane is a simple aromatic, alkane, and so its IR spectrum is relatively simple. You notice that there is nothing below 3000, so these are all C sp3 H bonds. And here we have only a handful of other peaks, so our fingerprint region is actually relatively simple, which come from CH2 and CH3 vibrations as well. Looking at the cyclohexene, we will see now that we have something above 3000, and this is the vinyl group, but we also have a lot of things below 3000 which come from sp3 carbons. And so this side shows us the CsP2 hydrogen, while this side shows us the CsP3 hydrogen. The double bond is over here at about 1700. It's a relatively weak vibration, which allows us to distinguish it from the carbonyl group, which also appears around the same time. And here you see that because of the relatively higher complexity of the molecule, you see that our fingerprint region has a lot more stuff in it, and again becomes very difficult to interpret. Let's look at a couple of more. The first example is an alcohol, and you can tell that right away because you see this very broad very characteristic shape of an OH vibration, which is also a very characteristic value of about 3400 here, and it's broad and strong. So this is characteristic of an alcohol. We also know that this is an alkyl alcohol because all of our sp3s are below 3000, so this is CsP3H. So we can tell this is an alkyl alcohol. And we also know that this is a CO stretching vibrations. So this is not very important for alcohols because we already know that since we have an OH bond. But this allows us to distinguish between alcohols and ethers because ethers only have this thing, while alcohol has this and the OH. The next example highlights that quite well. Again, we have now almost exactly the same spectrum. If you think about this, this part is the same, this part is relatively similar, this part is the same, but there is no OH vibration. And so since there is no OH group, this is probably an ether, indeed it is. Final spectrum would be that of menthone. This is a naturally occurring ketone, and again, nothing below 3000, so no sp3, no sp2 or no sp hybridized carbons with hydrogen on them. But there is a very strong, sharp vibration at about 1700. This is extremely diagnostic of a carbonyl group. And so we know from here this is a ketone with, and it's an alkyl ketone of some sort, and that's what we can. Finally, pentanoic acid and other carboxylic acids, they are basically not very different from simply combination of an alcohol and a ketone. And here is the carbonyl group. Here is the OH group. You see the broad peak over here. And here what you see sort of coming out of this broad peak is the superimposed group of CsP3 H peaks. So that's how we know that this is an alkyl carboxylic acid. And so this handful of spectra really show us that both the reach and the scope and the limitations of the IR spectroscopy, because we can figure out what the functional groups are, especially if you have very polar functional groups such as carbonyls, OH groups, or carboxylic acid. Right? We can also determine something about the hybridization of our carbons if they're bound to hydrogen. Okay, but there is really quite little that we can do beyond that, because IR spectroscopy will probably not be able to tell us the difference between this thing or an isomer, which will be this, because they would have the same functional groups, they will both have alkyl substituents on here, and IR spectroscopy really would not be able to help us distinguish. And so this again brings back the point that that we need a composite of this characterization technique. And we've seen that mass spectrometry provides us some information as to the size and mass of the molecule, but again, mass spectrometry either would not be able to distinguish between these two because it's the isomers. And that's why in the next lecture we will introduce NMR spectroscopy, which allows us to completely characterize both carbon and hydrogen skeleton, and at that point we remove almost all doubt as to the structure of a molecule. With this note, we will finish today's lecture on mass spectrometry and IR spectroscopy, and next time we'll get right into the NMR.